Thank you, Tina, for the introduction. Yes, so we are also part of this downscaling challenge, and not moving. Yeah, so our team consists of meteorologists and climatologists, and we're both working in more post-processing tasks. And our mentors are Mariana, Matthew, Andres, and Cornell. And yeah, I'm not going to spend too much time on explaining the downscaling challenge. I think the Spanish colleagues have given quite a nice overview of what the task is. And we have a bit of different workflow. So our approach is that we try to not use the classical normalization, but rather try to perform the downscaling on residuals, which means we first calculate the climatologies of both input and output, and then we calculate the residuals compared to the climatology and add some sort of seasonality. And this is then used in the downscaling. And we have three models or three approaches. One is called SAMOS, which is based on this idea of standardized anomalies and is a more statistical approach in downscaling. Then we will use a unit with adapted loss functions and a conditional GAN. And this will result in error downscaled, and then we have the verification. So to give you an idea of how this works with the residuals, here you see for one grid point for the whole time period of the training, the temperature curve, and this is what it looks like. And then we add and fit the climatological model, and this is done per time of the day we are downscaling and per pixel separately. So we calculate this really a per pixel model. So we have this fitted climatological model and then calculate the standardized anomalies. And this is what you get as anomaly. So you have this for every day and every hour used in this downscaling issue, you have a separate anomaly, and for every grid point, this you feed into the respective model, and you also train on standardized anomalies. And to get something meaningful back, you add the mean and the standard deviation to the anomaly forecast. And right now we are finished with the SAMOS approach. And SAMOS is based on ensemble model output statistics, which some of you might know. And the standardized anomalies also allow us to have this single linear regression for the whole domain. And on top, you see what is the ground truth. This is the error 5 input. And this is the mean predicted SAMOS output and the standard deviation. And this is for a case, in-sample case in January, and we have the same for an in-sample case in August. And the advantage of this approach is that you, in theory, can also draw ensemble members based on the ensemble mean and the standard deviation. And we did an in-sample verification. The out-of-sample verification for the test period is not yet finished. The colleagues didn't manage before holidays, but next week we will start the verification for the test period. But what you can see in the in-sample verification is that the SAMOS approach does already reduce MAE in RMSE quite a lot. So we have an improvement of above 20% here. And the results also suggest a good calibration. So moving to the next method, we aim at using a classical unit approach. We use here 5 input features: the temperature residuals, topography, and land CMOS information of the course, and the fine resolution. We implemented 4 different loss functions, or actually we used 4 different loss functions, MSE, MAE, and we also look at inversely weighted MSE and inversely weighted MAE. And we started with 2 model strategies because of the resources we were using first. We are not able to use the domain agreed with the Spanish team, so we had to use a sub-windowing approach. But we moved now to a different computing platform, so we will use the full agreed domain in one go without the sub-windowing. So what we also do is, or what I also did is looking at these residuals, and if I need to apply some sort of normalization as well. And these are residuals for selected dates at 0 UTC. And what we see is that we actually need to apply an additional normalization of the input data. And we will do this with the min-max normalization. In case you wondered, there are some strange features still here, and I need to look a bit more into detail if it's related to the calculation of minimum and maximum, or if the issue is somewhere else. Yeah, and what we also do and did implement are 3 different types of unit, which are slightly different in the configuration. So one unit is fit for this sub-windowing approach and used exclusively for this sub-windowing approach. And the other units differ a bit in terms of how many layers they have, where the skip connections are, what weight initialization they use, and so on. And what we also look into is if we're going to use the high resolution topography as additional target parameter or not. And this was shown in 2020 or 2021 in the paper, that adding the topography did in fact improve the downscaling results. So this is still on our list to look into. And what we have right now for the unit is we have a main code which calls either training or prediction. We have the normalization and some plotting functions in the utils. We have a generator depending on what type of unit and what type of approach you're using. You either have a generator for the sub-windowing and then a generator for the full domain. We have the custom loss function specified in a separate file, plus the units. And you call this model with arguments in the command line. And now I hand over to my colleague Sebastian, who will explain a bit the GAN approach.
Yeah, so for the GAN, we're currently in the implementation stage, so no results to be shown yet. So many of you are probably aware that there are different like ways how you can formulate GANs. There are a lot of different conditional GAN architectures that depend on what input you have or what kind of problem you want to solve. And the usual or a very neighboring approach to how downscaling, like from a phenomenological point of view, works is similar to how in computer vision, when you have a super resolving problem, or where you have an input picture in a low resolution and you want to increase the resolution with increased details in terms of how certain features in images are represented. And the specific architecture that we use as basis here is the SR, again, the super resolution GAN, or more specifically the enhanced super resolution GAN, which was just those are just a couple of subsequent developments that improved on their predecessors and improved the high resolution details that these certain GANs produced. And the input features and the setting in general, I don't read all of these points again, because they are similar to the unit basically. So similar with the upgraded computational resources, we can tackle all of the the domain at once, and we probably don't need to think about sub-windowing or patching within the model, which makes it easier. Yeah, and what we also play around, what we want to play around with in terms of the conditional is that you can use different input features, input images, like you would normally expect an input feature to be. But the special thing or way how conditional GANs are structured is that you can also supply conditional images into the model, which is input separately than the normal input features are. And this allows certain characteristics to be better captured. And what we want to experiment with is also that we don't use the high resolution topography just as an input feature, but to use it as a conditional. And yeah, the results, again, we are currently in the implementation phase, so we don't have any results to show yet, but we are very much looking forward to the next couple of weeks where we will get the first results. Yeah, next page. And this is already it with our short overview. So again, here we just have a couple of work steps listed. The SAMOS, the first modeling, our base that we referred to is finished, except for the out-of-sample validation. UNet is in its refining steps, and GAN is ongoing or in the implementation. And verification is obviously a parallel process that we will do until the very end. Thanks for your attention.
Thank you very much, Irene and Sebastian. Interesting insight also, you know, we had both ERA 5 or downscaling projects here in the session. And looking at the Q&A, there is a question from Florian Pinot. Why is it easier to train with the Wasserstein loss, faster to compute?
So usually in the very standard formulation of GAN, you have, like, for example, cross entropy that you use as loss, and you can run into these issues when you have the two distributions of the fake or of the generated fake distribution and of the real value distribution. You can have the issue that those distributions don't overlap and certain losses then don't have a gradient, and then you can't really perform gradient descents in the whole training process. And Wasserstein loss solves this issue because it can always generate a difference between distributions to formulate it in an easier way. And if the distributions don't overlap and are further away, then it will still just increase in value, basically. So you won't run into this issue of a zero gradient.
Okay. Thanks, Sebastian, for answering the question.